trying to read a book where every word has to be pre-approved by a librarian. That's kind of how today's language models work. They rely on tokenization to break text into chunks before learning anything. But what if the model could decide for itself how to slice up the text? In this paper, researchers from Carnegie, Mellon, and Cartesia AI propose HNET, a new kind of model that skips tokenization entirely. Instead, it learns to dynamically chunk raw byte sequences into meaningful segments, all while training end-to-end. No predefined rules, no space-based hacks, just a smart rotor that figures out where the natural breaks are. Even better, this dynamic chunking isn't just a cool trick, it actually helps the model scale better, learn faster, and even outperform token-based transformers twice its size. Let's unpack how it works and why it might change how we build language models.
Let's dive into the world of language models and tackle a common hurdle: breaking down text. Picture this. You're trying to read a book, but every word is chopped into tiny pieces. That's breaking down text for you, dividing raw text into manageable bits for models to understand. The authors introduce a technique called dynamic chunking, which learns to segment content based on context. This method replaces the usual breaking down text pipeline with a hierarchical network, or HNET, a kind of super smart brain that processes information in layers. This approach not only boosts performance, especially in complex languages like Chinese or even DNA sequences, but also makes language models more efficient and versatile. Continuing on, let's look at how this approach eliminates the need for breaking down text. The HNET processes raw data through stages, much like a machine that compresses and decompresses data. With dynamic chunking, the model decides where to cut or smooth data, similar to a chef deciding how to slice ingredients. This method optimizes segmentation strategies alongside the main model, creating an end-to-end, tokenizer-free system. This promises better performance without preset boundaries. Now take a visual tour of the HNET's architecture. Imagine two layers of processing. The first breaks down data into meaningful chunks, and the second reconstructs it. On the right, notice the dynamic chunking process, which uses a routing module to figure out boundaries, like a guide deciding where each sentence ends. A downsampler reduces complexity by keeping key information. Then, de-chunking uses a smoothing module to fill gaps, and an UP sampler restores the data. This smart system matches high-performing models by learning boundaries naturally, without preset rules. Let's delve into how HNET excels beyond breaking down text using hierarchical chunking. This builds higher-level meanings from raw data, like constructing complex ideas from simple words. You can stack these layers, making HNET super efficient and capable of handling complex datasets. This approach improves robustness against disturbances and offers better interpretability. Imagine the architecture of HNET like a U-Net, focusing on dynamic subsampling of data and learning everything end-to-end. It uses encoder networks, a main network, and decoder networks, allowing for flexible, scalable designs. Let's break down the HNET's processing system. Inspired by U-Net architectures, it compresses sequences into richer, smaller vectors, processes them, and then decompresses them back. Unlike typical methods, HNET dynamically sets chunk boundaries, optimizing data splitting and reassembly. The formulas show the data flow through encoding, chunking, the main network, and decoding. The network uses Mamba 2 layers for efficiency, focusing on compressed sequences and allowing larger networks without extra cost. This setup aligns with the strengths of transformer models, balancing computational demands while allowing flexibility. Now let's explore how HNET manages data dimensions and chunking. The model's depth increases without unnecessary layers by using efficient, powerful network layers. Dynamic chunking is a neat trick where the model learns boundaries during training, identifying meaningful data units. The routing module uses cosine similarity to mark boundaries by deciding where semantic shifts occur. The downsampler compresses data by selecting important vectors, while the smoothing module in de-chunking transforms chunks back, smoothing boundaries for better learning. This ensures efficient resource allocation while maintaining high-quality information. Let's talk about refining chunk boundaries during decompression. Imagine fitting puzzle pieces together. Sometimes they don't align perfectly. Look at Figure 2 to see how a smoothing module can improve this fit. Without it, chunks might misalign, causing errors. The smoothing module uses confidence scores to decide if boundaries should be strict or blended, like smoothing puzzle edges. This adaptive error correction prevents the model from learning poor patterns early on. An UP sampler then adjusts each piece to fit the original size, ensuring everything lines up smoothly. Now we get into techniques enhancing hierarchical sequence modeling, focusing on confidence scoring and gradient stabilization. The model uses confidence scores to decide boundary positions, promoting precise predictions. A key technique, the straight-through estimator, aids in stabilizing gradient learning. For upsampling, causal expansion maintains sequence flow, while confidence-weighted decompression uses scores to improve decision-making. Improved techniques include balancing normalization layers to maintain stable learning across layers. Information is split into streams, ensuring both detailed and compressed data flow effectively through the network. Let's explore how HNET optimizes data compression using a ratio loss method. Imagine it like a balancing act, ensuring the model doesn't compress too much or too little. The introduced formula helps maintain this balance, guiding the model to select the right data amount to compress. Inspired by techniques in expert models, this helps maintain efficiency. HNET adjusts learning rates based on input size, aiding effective adaptation and learning. During training, causal masking ensures correct data sequence processing, crucial for accurate outputs. Let's look at HNET's initial processing and token generation. During prefill, encoders create chunks, preparing everything for processing. Dynamic chunking modules use recursion to maintain a smooth information flow. When generating tokens, the model checks if deeper processing is needed, optimizing resource use. In the experiment section, HNET demonstrates its capabilities across datasets, including English and DNA, outperforming traditional models like MambaByte and LlamaByte. The architecture and chunking methods showcase HNET's improvements. Now let's discuss Table 1, which compares different model architectures, focusing on data and computational efficiency. It highlights how models like HNET and transformer variants handle data with various breaking down text strategies and compute budgets. The table details input types, breaking down text methods, and parameter counts, providing insights into each model's design and performance metrics. The experimental setup ensures fair comparisons, using consistent data and methodology, allowing us to evaluate each model's effectiveness in language tasks. Let's dive into language modeling and training strategies. HNET models, especially the two-stage variant, outperform traditional models using dynamic chunking. On a large scale, HNET variants show significant improvements over isotropic models like MambaByte. The one-stage HNET highlights context-dependent chunking benefits. As we scale to extra-large models, HNET starts slower but surpasses transformers with more data. This illustrates the strength of learnable chunking strategies, improving model efficiency and performance over time. Let's look at how HNET variants perform over time compared to other models. Check out Figure 3, which shows that as training data increases, HNET models, especially the two-stage variant, surpass others like transformers. They leverage dynamic chunking to improve efficiency. Table 2 highlights zero-shot performance across benchmarks, showing HNET's consistent accuracy edge. These results underscore HNET's smart resource use and adaptability with more data. The two-stage variant particularly excels, showcasing dynamic chunking and hierarchical processing's power. Let's focus on how well different models handle text changes. Look at Table 3 to see HNET's impressive robustness to disturbances like random case changes and repeated words, outperforming traditional models. The two-stage variant shines in adaptability. Visualizations reveal HNET's chunking aligns with intuitive boundaries like spaces, but adapts based on content, even without spaces. This flexibility shows HNET doesn't just rely on static cues, but understands the context and meaning, ensuring reliable performance across varied inputs. Let's explore how HNET determines text boundaries. Figure 4 illustrates that HNET, one stage, aligns with spaces, much like SpaceByte. However, HNET, two stage, starts with space like bytes, then intelligently chunks text into meaningful units, like words or phrases. This enhances semantic understandings. The discussion extends to alternate datasets like Chinese, code, and DNA, each with unique challenges. Chinese text lacks natural spaces, code has more white space, and DNA needs careful boundary setting. HNET's adaptability highlights its capability with diverse data types using dynamic boundaries. Let's highlight HNET's performance on Chinese and code datasets. Figure 5 shows HNET, two-stage, excels, outperforming transformers by handling languages without clear segmentation cues. It operates on raw data naturally, avoiding handcrafted features. The experimental setup maintains consistent parameters for fair comparisons. For DNA, HNET's hierarchical approach shows potential over traditional models. This adaptability underscores HNET's strength across languages and data types, leveraging dynamic chunking for efficiency and accuracy. Let's examine HNET's effectiveness on Chinese encode datasets. Table 4 reveals HNET, two-stage, performs better on Chinese, while both variants excel on code compared to transformers. Table 5 shows HNET's superior DNA performance, using less data for similar results. Figure 6 emphasizes efficiency, maintaining performance with reduced data. These findings underscore HNET's robust architecture and adaptability to different data types. Ablation studies further explore HNET's components, indicating design choices' impact on stability and learning efficiency. Let's dig into how different HNET components influence performance. Figure 7 examines removing the smoothing module, cosine routing, or the straight-through estimator. These elements are crucial for stable compression and learning. Figure 8 compares encoder-decoder setups using Mamba and transformer layers. The results show the smoothing module's vital role in consistent boundaries and stable training. Components like cosine routing enhance interpretability by detecting natural language patterns. These studies emphasize how each part of HNET contributes to robust performance and adaptability. Let's investigate how different encoder-decoder setups affect performance. Figures 9 and 10 show configurations with Mamba layers, like M4, excel in byte-level processing, outperforming pure transformer setups. The studies propose two hypotheses. Mamba layers either process fine-grained bytes more effectively or better compress information for subsequent stages. Results support the latter, showing Mamba layers excel in data consolidation, suiting hierarchical models. This efficiency in handling diverse input types confirms Mamba layers' crucial role for effective sequence processing. Let's explore hybrid architectures in HNET, combining Mamba and transformer layers. Figure 11 demonstrates these hybrids scale well, maintaining efficient data processing. Figure 12 compares HNET to mixture of experts models, showing HNET's superior capability regardless of parameter similarity. Findings suggest HNET's design principles, particularly Mamba layers, enhance performance by efficiently managing data flow and processing, even when mixed with traditional architectures. These insights underscore HNET's flexibility and robustness, adapting well to various configurations. Let's present a comparison of architectures, particularly those handling byte-level data. Table 6 categorizes models by autoregressive processing support, chunking mechanisms, and multi-stage hierarchies. HNET stands out for combining dynamic chunking with multi-stage hierarchies. This allows HNET to efficiently manage data, unlike models using static methods. These insights emphasize HNET's innovative approach in byte-level modeling, offering flexibility and enhanced data processing capabilities. Let's discuss HNET's comparison to mixture of experts models. HNET's performance isn't just about sparsity but meaningful data handling. The discussion highlights HNET's ability to distill from pre-trained models, boosting efficiency with limited training data. The architecture's dynamic nature flexibly handles different sequence lengths. HNET's hierarchical design enables recursive chunking for improved performance. While current models focus on individual layers, HNET's approach suggests future research directions in sequence modeling and architecture design. Let's explore several advanced concepts in model performance and scaling. Discussing latent test time compute, models like HNET can dynamically choose computation per byte, enhancing efficiency. Long context abilities are a potential area for HNET to improve, using its hierarchical structure. The page examines sparsity, noting HNET's dynamic sparing capabilities. Scaling is addressed, emphasizing understanding model behavior across sizes. Finally, it touches on bits per byte calculations, explaining how this standard metric may overestimate but still provides valuable insights into model efficiency compared to breaking down text models. Thanks for joining us today. Happy exploring together!